Yeah, I think we do. Share. So, good morning, everyone. If you're in the current, good afternoon, now. You're in the Dubai time zone. Thank you for those of us who have come today, and also those who are joining online. We've got a really exciting event for you today with two fantastic speakers. So, my name is Dr. James Kirk, and I work for WAIS, and I'm going to give you a quick 2.5 minute talk so far this week before handing over to our two wonderful speakers. So the main negotiations are now ongoing, and the main outcome of the first couple of days is the establishment and putting some money into the loss and damage fund, which was agreed last year at 27. As of this morning, it has about $600 million in there. $600 million. Yeah.
I was surprised with that.
Yeah, no, it's good. It has 400 million pledged in the first day. It's about 600 now by who can track it. So that's good. We have world leaders here today, and also yesterday. I saw Macron this morning walking along the streets. And whilst all the Bravo of the world leaders is going on, we have negotiations crunching ahead into the night as of last night as well. So the global stock take, the first one ever actually, which will be every 5 years, and reflecting on the progress countries have made in the spot, and so they're seeking how well have we done in the past and what we need to do in the future. So with that, we're turning to looking into the future, and one of the larger and some of the brightest for scientists is the West Antarctic Ice Sheet and the stability of this, depending on which measures we take. So this morning, we have two fantastic presentations, first by Caitlin Norton from the British Antarctic Survey, and then by Ron Rees from the Columbia University. And they're going to be talking about how stable the West Antarctic Ice Sheet is and the outlook for the future, because of the effects on sea level rise all around the world. So with that, I will pass on to Caitlin to start the presentations, and then the rest of the session will be chaired by Holly Hannah, one of our editorial researchers. So thanks a lot, and look forward to seeing you.
Thank you very much. Can you see my slides okay? I can't quite tell from here. Let me know when they're ready.
Just 10 seconds or something. So I'll let you know. Bear with us, we're just getting the slides up.
Could you reshare?
Still seeing a black screen, so just to touch base on that earlier point about the loss and damage fund. So 600 million sounds like a lot, but when you divide it up against the whole world and the various disasters, it's not so much. That's the other presentation. I think it was in Pakistan last year, for example, to about $15 trillion of damage here. So it makes really, it's a start for sure, positive progress, but still got a long way.
We switch the order of the presentations, or is
Perhaps better if it's not possible.
all right? Give me 5 minutes then. See if I can get it up.
Apologies to both speakers, we're just having a few technical issues on it.
With your logo,
Yes,
for an iceberg, normally 9/10 is below the water.
that depends how you interpret the logo.
Uh-huh.
Could just be a mountain, the ice.
Yeah.
Mountains are also very. Okay, our speakers are back on the screen.
Hello? 1, 2. Yes. Yes. Okay. It's working. Hi everyone, my name is Holly Han, and I'm an ECR through ICCI. And I'm a modeler in ice sheet and sea level, and so I'm really happy for the technical issue that I've experienced. So our first team in Nufton from British Antarctic Survey, and Caitlin is going to tell us about unavoidable future increase in West Antarctic ice shelf melting over the 21st century. So Caitlin, take it away.
Thanks very much. Hi, everyone. Thank you so much for having me here today. My name is Caitlin Naughton. I'm an ice, ocean, and climate modeler from the British Antarctic Survey, and I'm here to talk to you about West Antarctica and how it might change over the next century. Next slide, please.
Caitlin, are you with us?
I think you're in control of slides. Can you advance the slide, please?
Sorry, Caitlin, I think we lost you. Okay. Can you
There we go.
Yeah.
We can work with that. Okay, so look, the West Antarctic Ice Sheet is losing ice at an accelerating rate, and we can see this in the satellite record. It's responsible for almost all of Antarctica's contribution to sea level rise. Next slide, please. If we look in more detail at the satellite record, we can see that the ice loss is driven by ice shelf thinning. Ice shelves are the floating bits of the ice sheet around the edges, and they hold back the flow of the glaciers. We call this process buttressing. If you thin an ice shelf or remove it entirely, in almost all cases, the glaciers behind it will speed up their flow towards the ocean, and that's what causes sea level rise. So these ice shelves in West Antarctica are thinning, and they're thinning from below. They're being melted by the ocean from the bottom up faster than they can regrow. Next slide, please. West Antarctica is vulnerable to the ocean because most of the ice sheet in this region rests on bedrock below sea level. And everywhere that's below sea level, there's the potential for the ocean to one day melt its way underneath. It's a lot easier to melt the ice sheet using the ocean than using the atmosphere. First of all, the ocean is a lot warmer than the atmosphere in Antarctica, but also the water has a much higher heat capacity than air. It's very efficient at melting ice. So we're quite concerned about West Antarctica because there's a lot of ice there that could be in trouble even if climate change doesn't progress much further. If the entirety of the West Antarctic ice sheet melted, we would get about 5 meters of sea level rise. Now, we don't expect the entire thing to melt, and if it does melt, will take centuries to fully respond. So the big question is how much is actually going to melt and how quickly? Next slide, please. A big piece of uncertainty here is what the ocean will do. I mentioned earlier that ice shelf melting in Western Antarctica is driven by the ocean. Modeling experiments suggest that the ocean in this region, called the Amundsen Sea, may have warmed over the 20th century in response to climate change. Unfortunately, we cannot verify this with observations because observations of the ocean here only started in 1994 and have a lot of decadal variability. So it's too soon to detect a trend. But regardless of whether or not there was a historical trend in ocean temperatures, if the ocean warms further in the future, it can only mean bad news for the ice shelves and ultimately sea level rise. Next slide, please. If you're studying the future, your only option is to use models. And until now, we have very few model projections of how the interactions between the ocean and the West Antarctic ice sheet could change in the future. This is because the Amundsen Sea is very hard to model. It needs very high resolution, and the ice ocean processes are also not represented in the global climate models used by the IPCC. So we have to use regional high resolution ocean models specialized for this part of the world. Until now, the only future projections using models like these were looking at the worst case scenario, RCP 8.5. I happen to have a very nice model of the Amundsen Sea, and so I decided to use it for some more comprehensive future projections. Not just of the worst case scenario, but also the best case scenario, the most ambitious targets for the Paris Agreement, as well as scenarios in between. Next slide, please. And what I want to know here is how much control do we still have over ocean warming and ice shelf melting in West Antarctica? How much can still be prevented if we reduce fossil fuel emissions in time, and how much is now committed? And how long before the different scenarios diverge, before the results of our actions become clear? Next slide, please. Unfortunately, the results are not particularly cheerful. In all scenarios, we simulate a widespread forming of the Amundsen Sea and an increase in ice shelf melting. These are the trends until 2100 in a 2 degrees global warming scenario. And the black dotted line shows the continental shelf. So everything south of that line is the shallower bit of the ocean, which has direct access to the ice shelf. Next slide, please. What's the process causing this ocean warming and ice shelf melting? It all has to do with the water mass closer compared to deep water. This is relatively warm water, about 1 degree Celsius, so you wouldn't want to go swimming in it. But in terms of Antarctic oceanography, 1 degree is very warm indeed, and it can melt ice very quickly. It usually sits offshore a few hundred meters below the surface, and it doesn't directly impact most of Antarctica. But in the Amundsen Sea region, it flows onto the continental shelf through a series of subsurface ocean currents. And here it directly accesses the ice shelves and causes rapid melting. What's happening in our simulation is all these subsurface currents are getting stronger and more circumpolar deep water is transported onto the continental shelf. We're still unpicking all of the atmospheric and sea ice processes which cause these currents to speed up, but the fact that they are speeding up and that it's in response to climate change is very clear. Next slide, please. So now let's compare the different scenarios. We find that even in the best case scenario, 1.5 degrees global warming, the ocean warming and ice shelf melting trends are about 3 times larger over the 21st century than over the 20th. That means the changes we've already seen are expected to accelerate by about a factor of 3. This is a box plot of the trends in every scenario, and the boxes and whiskers show the spread. Every scenario has a range of possible trends. That's because we accounted for the uncertainty due to internal climate variability. Natural events like El Nino and the interdecadal Pacific Oscillation have a really big impact on the Amundsen Sea. So just the timing of these natural climate events can actually change the warming trend by up to a factor of 2. Next slide, please. The uncertainty that this introduces. Oh, previous slide, please. That's the one. Thank you. The uncertainty that this introduces means that the 3 lower range scenarios, so a 1.5 degree world, a 2 degree world, and RCP 4.5, are statistically indistinguishable. Based on the ensemble spread, you cannot say that there is a significant difference between them. So you can interpret this as saying the only control we still have is to prevent the worst case scenario, RCP 8.5, because it's the only one where the warming is significantly different. Next slide, please. As well as trends, we can look at time series of how the ocean temperature evolves over time. And you can see that the 4 scenarios are very much overlapping for most of the 21st century. Another statistical test we can do is to ask when RCP 8.5 diverges from the other scenarios. When does it become distinct? And we find that that happens around 2045. So for the next couple of decades, which could be a really crucial couple of decades for the glaciers, we probably have essentially no control over ice shelf melting in the Amundsen Sea. The main determinant of the precise amount of warming and melting will be the natural climate variability, which we cannot predict or control. Next slide, please. One more thing about this graph, you'll see that the coolest scenario, 1.5 degrees in blue, starts to flatten out towards the end of the century. And we find that although the long-term trend is not significantly different, the running mean does diverge from other scenarios in about 2059. This suggests to us that the scenarios are likely to diverge more in the 22nd century and beyond. So we probably do have more control after 2100, but that's a very long time scale for policymakers, which I'll come back to later. Next slide, please. The question everyone wants an answer to is how much will the sea level rise in response to this ocean warming and ice shelf melting? I unfortunately cannot give you a precise answer to that because our model doesn't include all the necessary processes like ice sheet dynamics and snowfall accumulation over the ice sheet. We just simulate ice shelf base melting, and while that is currently the process driving sea level rise from West Antarctica, it's only one term in the equation. Next slide, please. What we can do instead is to look at the spatial distribution of ice shelf melting, because not all ice shelves are created equal. Some regions are more important than others in terms of their impact on sea level rise. Here is a map of something called the buttressing flux response number, which is a really valuable concept developed by our next speaker, Rania. What it says is, if you take one little pixel of the ice shelf and you thin it by a given amount, how much will the glacier speed up in response and how much sea level rise will occur? So smaller values shown in white and yellow are regions where ice shelf thinning isn't so important for sea level rise, while the larger values in red and purple show regions where ice shelf melting is really important for sea level rise. These are the areas that we really don't want to lose. Next slide, please. So what I've done here is express my results for ice shelf melting in terms of the buttressing flux response number. On the left here, it's ice shelf melting trends in regions with high buttressing. As you go to the right, it shows regions, sorry, on the left is regions with low buttressing. As you move to the right, it shows regions with high buttressing. And the different colors show the different scenarios. And you can see that compared to the 20th century in gray, ice shelf melting increases across all buttressing classes and in all scenarios. So the less important ice melts more, and so does the more important ice. Next slide, please. Another thing to notice is that the difference between scenarios, particularly between RCP 8.5 in pink and the others, becomes smaller in the more important regions. And this says that the additional ice lost in RCP 8.5, which is the bit that we can still prevent, is disproportionately among ice shelf that are less important, while the melting of the more important ice is already locked in. Next slide, please. So in summary, it appears that we're committed to a rapid increase in the rate of ocean warming and ice shelf melting over the rest of this century. Next slide, please. On this timescale, reducing fossil fuel emissions has very little impact. The only control we have is to prevent RCP 8.5, which we're already doing. Next slide, please. We can't say exactly how much sea level rise would happen in response to these ocean changes or how quickly, but it's clear that rapid ocean warming will only accelerate the ice loss that we've already observed. Next slide, please. The main uncertainty in our results is that we can only use one model. In climate science, we like to use multiple models wherever possible, and I hope that over the next few years, the community will continue to develop more models with this sort of capability and to repeat experiments like these ones. Next slide, please. So what are the implications for policy? This study underscores the importance of adaptation in the fight against climate change. Even a 1.5 degree world, which is probably the best we can hope for, is a big change compared to pre-industrial. And there are some impacts of climate change which can now no longer be avoided. In this case, I think it's time to start seriously planning for multiple meters of sea level rise over the next few centuries. This is from all sources, not just West Antarctica, but West Antarctica will play a growing role as time goes on. Next slide, please. This is in line with the latest IPCC projections for sea level rise. Even under the best case scenario, there's a reasonable chance that we could have several meters by 2300. This is even before the results of my study. The risk of this outcome is sufficiently high to be worth planning for. Ice sheets are slow-moving beasts, so the changes that we've seen so far are small compared to the sea level rise that's coming. Next slide, please. I also want to emphasize that mitigation is crucial. Our results in no way undermine the importance of mitigation in the fight against climate change. But for the West Antarctic Ice Sheet, our results suggest that mitigation only has an impact in the very long term, after 2100. So we need to shift our focus to that longer time scale because that's when we really can make a difference. Next slide, please. Thank you all very much for listening and for having me here today. I believe we're going straight to the next speaker and saving questions for the end, but I'm very happy to answer questions at that point. Thank you.
Thank you, Caitlin, for the great talk. There's a 3 seconds lag between the audio and the camera, so apologize for that. Do we have any questions from the audience? Okay, so should we then just go through the whole talk and then have a panel session? Sounds good. Okay, so our next speaker is Rania Rees from Northumbria University in Newcastle. And Rania is going to tell us about the West Antarctic Ice Sheet stability at the current status. Rania, take it away.
Yes, can you hear me all right? Can you hear me all right? No? Sorry, can you give me a sign if you can hear me?
Can't hear.
Yeah, okay, cool. Okay, then let me start. Okay, so thanks a lot to Caitlin for the great talk. And I want to continue now talking about the West Antarctic Ice Sheet, in this case about tipping of the West Antarctic Ice Sheet. And this is based on work that's been published just this year together with a number of people within the TIPAX project. And you can see all their names here. So Caitlin also contributed to this work. And the main motivation behind this work is really that the West Antarctic Ice Sheet is considered a tipping element in the climate system. And this is because ice loss from West Antarctica is going to raise sea levels globally. So that's going to impact global coastal regions worldwide. And we know that West Antarctica is losing ice at the moment. Caitlin already mentioned that the ice sheet is losing ice at the moment. And this map shows the regions where this ice loss occurs. And this is mostly in regions that are dark red. So particularly here in the Amundsen Sea region, in this area, ice loss is pretty pronounced. And we know that the total volume of the West Antarctic ice sheet is about 5.3 meters of sea level equivalent. So if the ice were to melt down completely, this would raise global sea levels by about 5 meters. East Antarctica has about 10 times the volume, so more than 50 meters. However, there's less changes observed in the East Antarctic ice sheet at the moment, and the focus really lies on West Antarctica. And in West Antarctica, the focus is particularly on the Pine Island Glacier, which is shown here in this area, and the Thwaites Glacier next to it. So these are really two big glaciers that have been changing or are changing a lot at the moment. And in particular, these changes of the glaciers have raised the question whether a tipping point for collapse of West Antarctica might have already been crossed. And before we look into this question, I want to dive into how we understand tipping in West Antarctica. And this here is an excerpt from a video we made within the project, which shows schematically how tipping works. So we have here a side view of the ice sheet with the bedrock, the ice sheet sitting on the bedrock, in this case below sea level. So this is our sea level. And we have the ice shelf, which is the floating extension of the grounded ice sheet. So the ice flows from the grounded ice sheet towards the ice shelf. And at some point, it becomes so thin that it starts to float. And this region is quite important. It's the so-called grounding line. So the grounding line is the area where the ice starts to float on top of the ocean. And the grounding line is an essential indicator for the health of the ice. And in general, when ocean waters warm, as Caitlin has been discussing before, this will cause the grounding line to retreat and ice to be lost. As you can see, this process here is a gradual one. However, there are tipping points in the ice sheet at which this process becomes self-accelerating, as you can see here. So the ice loss accelerates substantially, and also it becomes self-reinforcing. And this process is the so-called marine ice sheet instability. And how you can understand it is basically that there is a positive feedback mechanism where the flux across the grounding line, so all the transport of ice across the grounding line, when that increases, it will cause the grounding line to retreat. And in this case, when we have the grounding line retreating and this feedback is at play, this will cause enhanced flux across the grounding line. So you enter a self-perpetuating feedback mechanism that will cause the grounding line to continue retreating, even if you stop forcing it. This is often displayed in this way. So in this case, we show the ocean temperatures over the grounding line. Maybe you have seen this type of figures before. And if we assume that the ice sheet is sitting somewhere here, so we have rather low temperatures in the ocean and the grounding line is quite advanced. What happens is when the ocean temperatures now increase, the ice sheet will move along this solid black curve towards the tipping point. And this is what we saw in the first part of the video. So the grounding line is gradually retreating. But once it hits the tipping point, there is no way it can evolve any further along that line, and it basically falls down onto the second branch down here. And this is what we saw. This was this fast self-perpetuating retreat that's caused by this positive feedback loop. This type of tipping is called irreversible, because to reduce or to regrow the ice sheet, ocean temperatures have to be reduced quite a lot. So let's look into that. There is something missing. Okay, so to regrow the ice sheet, one would need to reduce ocean temperatures all the way down here until you hit this point, and then the ice will regrow again. And this is usually called an irreversible process because it's not enough to just reduce ocean temperatures below this tipping point, but you really have to take them much further below. And this is, if we think about it in reality, this is, of course, makes a gigantic difference, right? And it might not be possible to actually do that in reality. So tipping in West Antarctica is really understood as the onset of such an irreversible grounding line retreat that is driven by this positive feedback mechanism. And if we talk about West Antarctica, we talk about irreversible retreat over large regions of the ice sheet. This is the regrowth. And we know that this can happen. So this has been shown, for example, in a study here from 2021, where we found that for Pine Island Glacier, you can actually have 3 such tipping points where the grounding line retreats. And this gives exactly this figure we've seen before. So we've seen like this hysteresis loop, and we can see it 3 times here. So there are actually, in this Pine Island Glacier, you can find 3 such smaller tipping points. But of course, when we talk about the West Antarctic ice sheet, we're interested in a large-scale tipping point that can cause the retreat of the whole ice sheet. And there's going to be a paper coming soon, I think on Monday, from members of the group I'm working at about tipping in the past. So watch out for that. And we also know that the West Antarctic ice sheet has this tipping behavior. So the video is going to start again. In this study by Feldman and Leverman, they showed that a small perturbation in the Amundsen Sea region here and can already drive this positive feedback loop that I described before to lose basically all the marine regions of West Antarctica. Importantly, this happens over very long timescales, right? So the timescale here is tens thousands of years. So we know that this instability mechanism exists. And in this paper by Garber et al. From 2020, they showed also that on a much larger scale, the whole Antarctic ice sheet has this hysteresis behavior. And they found that the tipping of West Antarctica is possible between 1 and 2 degrees above pre-industrial temperatures. So we are already there, right? We are already above 1 degree. So we might already be in this tipping range. And we know that grounding lines in Antarctica are retreating. So this map shows the regions where grounding lines are retreating. And what sticks out again is the Amundsen Sea region, where we see most of the ice flows and the grounding lines are retreating at the highest rate at the moment, right? So this really raises the question if the ice sheet has already tipped or not. And to analyze this, I worked together with colleagues, and we used 3 different ice sheet models, ELMA-ICE, UA, and PISM. And we went to analyze this question because to understand or see if tipping has already occurred, you can't just do that from looking into observations. You really need some dedicated model experiments, a bit what Caitlin said before about understanding the future. The same is true for understanding irreversibility of retreat. So we all set up the models to look as close to the current Antarctic ice sheet as possible, to have the grounding lines in the best places or as close as possible to the current grounding lines. And then we made a set of dedicated experiments which are designed like this. So we basically perturb the system, the grounding lines in this case, by increasing the ocean temperatures, melting the ice shelves faster. And we perturb it such that the grounding lines are moved a little bit. So we have actually a significant perturbation to the grounding line. So they retreat a little bit, and then we remove the forcing, and we analyze the system response after that. So if we find that the ice will continue to retreat, that hints at that there is this positive feedback at play, because only this positive feedback can drive the continued retreat because the ocean warming has been gone. On the other hand, if the system recovers, there is no such self-sustaining retreat, and hence no marine ice sheet instability at play. So we ran these experiments for all around Antarctica, and this is just example for Pine Island Glacier and Thwaites glaciers. The dotted lines are the initial positions. The red lines is after the perturbation. So we get some retreat of the grounding line, thinning of the ice shelf, thinning of the grounded ice. However, we find that, and this is this blue line here, that the ice regrows to its initial position after we stop the perturbation. So the grounding line is reversible. And we found this for the 2 glaciers, but also in all 3 models that we tested. So in all cases, the grounding line is reversible, and we found this also be true all around Antarctica. So all 3 models do indicate that there is no marine ice sheet instability-driven irreversible retreat in Antarctica at the moment, which is good news, right? So we're not yet in this position where the West Antarctic ice sheet has tipped. However, we know that grounding lines are retreating at the moment. So we could ask the question what this means, like how far are grounding lines retreat? Where could this lead to? And to analyze this, we made another set of experiments. In this case, was just 1 model, where we keep just the current climate constant. So we just assume that current climate conditions stayed the same, and we run this experiment in the model forward for 10,000 years, so a very long time, because this can allow us to understand what the grounding line position or the grounding line wants to move to in the current state of the ice sheet. And then we do reversibility experiments, again, like before, but now on much longer timescales to test for reversibility or irreversibility of this. And in this case, we run an ensemble of different states, and you will see them in the next slides again. We had 15 different members to test for parameter uncertainties in the models, to test for this a little bit. This is our initial state. So we find the representation of the present day ice sheet. We find mass losses in this area which are a bit underestimated. So what we will find is maybe an underestimation of what might actually happen. We find mass losses in the big ice shelves which are a bit overestimated, so this might not be realistic in the following. And if we just keep the current climate condition constant, what our model tells us is that we find large-scale retreat in the West Antarctic ice sheet. So all these areas that are red, dark red here, are regions where the grounding line is going to retreat under the current climate. So this is true in Thwaites Glacier for 15 of the 15. So all our grounding, all our present-day configurations show retreat. This is true in some cases for Pine Island as well. Okay, so we find really large-scale retreat in the West Antarctic ice sheet under these conditions. We tested for irreversibility to see if this is really related to marine ice sheet instability, and this seems to be the case. Because all these regions stay red. So this is really a retreat related to marine ice sheet instability in this case. How much and how fast is this? If we look closer into the change in ice volume, we find that over this 10,000 years, the West Antarctic ice sheet loses between 2.7 to 3.5 meters of sea level equivalent, so about the 3 meters of sea level rise that we get from marine regions in West Antarctica in general. And we can also see that this process is, lucky for us, rather slow. And we have a maximum rate of ice loss of 0.7 to 0.9 millimeters per year. So this is about 3 times the rates of ice loss we have in Antarctica at the moment. So it's an increase, but maybe a manageable rate. We can also ask ourselves, when does actually this irreversible retreat start? And this shows just 4 different possible configurations, and we tested the reversibility at different points in time. And what we find is that the earliest onset of irreversible retreat, so when this tipping really kicks off, is between 300 and 500 years in. Whereas, but this is not consistent. So as other model simulations show that this irreversible retreat starts later than 10,000 years. So we can't really pin this down. It's very uncertain when this irreversible retreat is kicking off in the model simulations. There are some processes that are important for this question, but that are not included in this case. One is the bedrock uplift. So when the ice load is removed, the bedrock's going to come back up, and this can slow down retreat or even stabilize grounding lines. So we didn't include that, but there is a model simulation from Gollich et al. 2021 where they showed that actually, even with this process included, they expect continued ice loss in West Antarctica. Another process we did not look into and did not include here is calving, related to ice shelf failure, ice shelf collapse, calving. All these things are not included, and I would expect all these processes to speed up the retreat. So how can we understand these results? If we go back to this initial typical tipping curve, I was talking about the ice sheet moving along the solid black lines, but what actually happens is that the ice sheet is not moving along these solid lines because it's not because its response time scales are very slow. And so what I think is the case here is that the ice sheet is maybe in this state what we call somehow committed instability or an overshoot state, where if we simply wait and keep the ocean temperatures, the climate conditions constant, the West Antarctic ice sheet is going to retreat irreversibly. However, it can still be reversed. So it's still possible if climate conditions were reduced again to go back to the safe state up here. So it's this is sometimes called an overshoot state. What does this mean in terms of the results Caitlin showed before, where she showed that very worryingly ocean temperature in the Amundsen Sea region is expected to increase even further. And this would mean, because what I did show before was done under current climate conditions, right? So if the ocean drives more melting in the Amundsen Sea, this will shorten the time scale until when the irreversible retreat is starting, and as well make the whole collapse of the West Antarctic ice sheet faster, of course. How fast, we don't know. So I put in this study by Sun et al. From 2020, where they made a model intercomparison project. And importantly, this is a very unrealistic thing, right? Because they assume that whatever floating ice you have, it's directly removed, either carved off or melted away. That's the two difference between these experiments. And they found that in this scenario, between the ice sheet models, the West Antarctic collapse can lead to 1.9 to 5 meters of sea level rise in 500 years. So on average, that would be a maximum rate of 1 centimeter per year, right? So this is a really high rate. But importantly, again, this is an unrealistic upper limit, because in reality, it's not going to happen that all the floating ice is just immediately melted at very high rates, even higher than what Caitlin projected. Or so unrealistically high, or removed directly. Okay, it's just an idea to get an upper limit for this process. So to summarize, we found, using 3 different ice sheet models, that there is no indication that we already have irreversible retreat or cross the tipping point in West Antarctica at the moment. And this includes Pine Island and Thwaites glaciers as well. However, we found that the current climate conditions can be enough to eventually lead to this irreversible collapse, simply because grounding lines are retreating at the moment, which would eventually mean 3 meters of global sea level rise. And this was shown only in 1 model, so it's a bit less confirmed than by 3 models. But it shows that, we might already be in this overshoot state in West Antarctica. We found that the earliest onset of this irreversible retreat is 300 to 500 years from now. But importantly, this is under current climate, right? So we saw Caitlin's result, which would potentially speed up the whole process substantially. So implications from that is, well, there is going to be further sea level rise from West Antarctica. it might be already on the way to collapsing. So there is a need for adaptation. However, the timescales are really important. And how fast this is going to happen is really, I think, still an open question. But what would be expected from model experiments and everything is that, of course, the stronger the forcing, the stronger the warming, the faster the retreat, and also the onset of this irreversible sea level rise. So thanks a lot from my side for listening. And if you want to see more, there are videos on YouTube that explain the experiments.
I think Ronja said something, but there's a sound delay, so we can hear you.
Oh, I just said there are YouTube videos to dive more into this.
Oh, I see. I see. Alright, thanks. So I think that was there's. Oh no.
I believe you're muted. Sorry, we can't hear you.
Melt into the seas around the Antarctic might be significantly changing the salinity, which will affect the currents that circulate in that area and potentially either affect the marine food chain or the likelihood of water getting under the ice sheets. So it's basically a question around the salinity problems that are the freshwater melt into the ocean, and if that's an issue or not.
Really good question.
I didn't think it was. So it may be an out-of-scope question. I was just curious.
Yeah, I can take this question. Can you hear me okay?
Do you mind turning the volume up on that?
Well, don't worry about it. I was just curious about that first.
I'm happy to respond. Just I'm not sure if you can hear. Let me know if it's okay to get started. I only heard the second half of the question, but maybe you can pick it up the first half. Okay, I'll just respond and stop me if it's not working. Yes, so I believe you're asking about the impacts of the freshwater release from melting of the ice sheet, glacial meltwater. This is something that we're concerned about. It's not that well understood, but there are concerns it could slow down the global overturning circulation, reduce the rate that salty, dense water sinks from Antarctica and spreads out through all the rest of the world's oceans. There's also concern that the fresh water from the Amundsen Sea melting could travel downstream and cause freshening in the Ross Sea sector. We're already seeing this, and we've been seeing it for about 60 years. There's concern that that freshening could itself destabilize the Ross Sea sector of the ice sheet by flipping it from a cold to a warm state. It's unclear how close we are to that transition. It probably isn't immediate, but it could happen with enough fresh water. In terms of biological impacts, I'm not a biologist, so I can't really speak to that, but I'm sure that there would be some effect of a change in salinity on the ecosystems.
I have one question for Ronya. I actually had two questions, but you've already answered one question in your one of the summary pages, so that's all good. I was interested in seeing your plot showing the average of melting the grounding lines in the compared to that machine grounding lines and of the control runs. And in the Thwaites region, did I see it right that the grounding region in the model simulation are pretty similar to that machine? And if that's right, then shouldn't it see some retreating in grounding line in the Thwaites region? And why do you think that didn't happen in your control run?
You're talking about the first part, I think, of
Sorry,
the experiment.
Could you start responding in like 3 seconds since there's a lack of
Okay.
delaying value, so I'll turn it on.
Okay, so the question was about the grounding line positions and the retreating of the grounding line, if I got that right. This is important because the first part that I talked about that we did with the 3 models, there we really made sure the grounding line is close to present state. But we made also sure that the system itself is not retreating in that case because we want to make this experiment. So this is really a theoretical approach to doing that. However, in the second part, right, we saw that we have the grounding lines retreating, in particular in the Amundsen Sea region in Thwaites in Pine Island. If we put that into the model, then it runs eventually into this irreversible retreat. Not yet, but eventually.
Last call for any more questions? Thank you so much again for our speakers, Caitlin and Ronya. We appreciate you bearing through our technical difficulties. As for the audience as well, it's been a pretty tough session, but I'm really glad that we pulled it through to the end. So we appreciate your patience, and I really hope that you enjoy the rest of COP28. And thank you again, speakers.